So last lecture, we start with coding for channels with state. This is the so-called Gelfand-Pinsker problem. In this problem, we look at a channel which is like a discrete memberless channel. The difference is that we have a discrete memberless source which produces a sequence Sn, some kind of state sequence, which interferes the channel. So the channel depends on this sequence. The problem can be described as follows. So an encoder wants to send a message W to the receiver by mapping it into the sequence Xn, like for the discrete memberless channel. But now the channel Py under the condition X and S has interference in the form of a sequence Sn, which is output of a discrete memberless source Ps. So the letter S presents somehow the state of the channel. And the encoder has access to the interference Sn in a non-causal fashion. That means that the encoder knows Sn before he encodes Xn. Now the goal is to design the encoder and decoder to maximize the rate while ensuring that the error probability can be made arbitrarily small. Our goal is to calculate the capacity. This is the supremum over all achievable rates. It turns out the theorem that the capacity is the maximum over all channels from S to U and all encoding function, later I should be here in F, not in X, the maximum over the mutual information of U and Y minus the mutual information of U and S. As you notice that we again use an auxiliary random variable like we did in the problem before. So to get the achievable region, we consider such a random variable U with alphabet U. And we assume that U is the output of a channel from S to U. So that's the state to our auxiliary alphabet. Now we define a function f. Oh, unfortunately, I wrote here an x, it should be also an f, that maps the symbols u and s to x. So depending on the u, which will be in our coding book, and the state, we send letter x over the channel, which is the input alphabet. So the sequence xn will have as individual letter xi, depending on the function f, ui and si for all I. And then we can write the mapping at x to the n equal f to the n of u to the n and s to the n. Now in our code construction, we use again binning. So we generate 2 to the n r plus r prime code words, un, so we use the alphabet u, or our auxiliary alphabet, and it's depending on W, that's the message, and on V, that is the size of the bin. And we choose all symbols in the codebook independently and random according to the random variable U. Now, how is the encoding procedure? We look at an encoder. So given a W, that's a message, and the whole state sequence. So he tried to find a V such that un from W and V tilde and Sn is jointly typical. So W chooses the bin because it's the bin for the code word, and the interference somehow selects the V tilde. If one finds now an V tilde, then we choose V equal V tilde and transmit this Xn. If not, then we just transmit something. But we just must have a rule what we transmit if we don't find such thing. This is a kind of error. Now what did the decoder do? He receives some Yn, and he also has the codebook. So he look at the codebook, and he is searching now for W tilde and V tilde, such that un of W tilde and V tilde and Yn is jointly typical. If there's one or more such pair, then we choose one and put out the corresponding W tilde as our estimation of the messages W hat here. If there's no such pair, then we estimate it by message 1. What was the idea of the proof? In the proof, we also go through the different events. So the first event is that the state sequence is not typical, and we know that this probability goes to 0. The second event is that the state sequence is typical, but we don't find a V such that a code word and the state sequence is jointly typical. Of course, we can avoid this when we choose a bin big enough. And we showed that if we choose a R prime greater than the mutual information between U and S, then this error probability is small. The third event is if the code word UN and the state sequence is jointly typical, but UN and YN is not jointly typical. But there we show by the properties of typicality that this event also approaches 0 if n goes to infinity. The last event is that yn is typical and the decoder finds a W tilde and V tilde, but W tilde is not equal to W. And the UN of W tilde and V tilde and YN is jointly typical. That means again an error. And to avoid this event, or we want to have that this event goes to 0, we must have that R plus R prime is smaller than the mutual information between U and Y. Now, if we put these two things together, then we have that our rate we can achieve is the difference between IUY minus the mutual information of U and S. That's just here, we have this rate, and we put here for R prime, we put here in the mutual information of U and S. Of course, we can choose any channel we want here, and we can choose every function we want here. And when we want to maximize this, so we can maximize over all auxiliary channels and over all possible encoding functions.